So today we're really happy to have Elias Most here. Elias got his PhD in 2020 from Goethe University. All right. And since then has been at Princeton in their physics department. He's now the John Archibald Wheeler postdoctoral fellow. Is that correct?
That's right.
Yeah, excellent. And next year you're going to be starting a faculty job at Caltech?
Yes.
Yes. Excellent. I have all my facts correct. He's going to tell us today about the theory of neutron star mergers.
Right.
Thanks.
Thanks so much, Mike. Thanks everybody for coming. No, you've got your phone, right?
Yes.
Okay. Today I want to chat a bit about what happens when two stars collide. If I manage to get the message to disappear from my screen.
Right. Everybody can see the slide, but you.
No, I can see the slide. There's just a lot of stuff in front of it, and I cannot see my mouse, which has disappeared.
It's on the Zoom window.
It's on the.
No, that's a different mouse.
That's a different one.
Apologies.
Interesting. I can't see it either.
No.
Certainly not without my glasses.
Oh gosh. No, something there just.
Let me
not
test
working.
something.
Yep. Sure.
No.
This thing crap.
No, it doesn't.
I have to add, it's a completely new laptop. It's the first talk I'm giving with it, so something clearly does not. Okay, so
so you can move forward.
Okay, but that's fine. I mean,
right.
we can just not move backward, or we can move backwards, but we cannot select individual slides. So just respond to your question. What I want to chat about today is what we can learn about the densest states of matter from the collision of two neutron stars. As the picture might indicate, I'm working in numerical simulations, and so this is what I will largely use to motivate what we're doing, but I try to focus on three different areas using them. The first one will be, I try to give you some overview of what happens in a neutron star merger and what we know both from observations and also from theory, and then I want to tell you some directions you could apply that both in nuclear physics, but also in the extreme plasma surrounding the neutron stars and making connections to, let's say, radio transients right before the stars collide. And so today's talk then will proceed in those three stages. We'll largely focus, because my background, so what I should add is, if you've never heard about Goethe University, they're basically right next to the largest heavy ion collider that they're constructing in the world. So my background comes more from sort of working not directly on nuclear theory, but working with people working on nuclear theory. And so I'll take kind of that as the main subject. What can we learn about neutrons, protons, and the dense matter equation of state from the collision of two neutron stars, in particular when you add finite temperature and neutrino effects. We will do this in part by looking in what imprints is left by gravity itself in the gravitational waves being emitted from the collision of the two stars. And then finally, we'll go over and make some connections with what else you can do with two neutron stars when you consider sort of the surrounding of the star. Okay. And since I know this is a very interdisciplinary center and we have many people with many different backgrounds, I thought I'd spend at least 3 slides just for the purpose of this talk, saying what our protagonist of today is, and this is a neutron star. And what we'll focus on largely, and we'll actually see in a minute on what happens if we start that movie, this animation, and the two neutron stars begin to orbit, but really the protagonist of today is this yellow gooish thing, the neutron star itself. And if you've never heard about the neutron star, which I'm sure many of you have, but just, if you want to get your facts straight, if this is us at 726 Broadway, and I put the neutron star just in contrast, it's about the size of the island of Manhattan, slightly covering Jersey City over there. Okay, so a diameter of 20 to 30 kilometers. In terms of mass, if you wonder, well, what does the thing look like? Well, it's as massive as the sun, or as 2 times of the sun. Depends a bit on what stars you look at. So does it really look like this? Are we all going to get radiated away? Are we kind of getting a massive sunburn? The answer is probably not, or probably we would if the thing would be so close, but that's actually not what we would see if we could get as close and survive. Rather, what you would see, depending on how fast those stars can spin, so if you think in terms of a millisecond pulsar, you kind of see a spotty and stripy feature. This is some work with people at Flatiron that we've been kind of doing over the past years. But really what is interesting for the purpose of this talk, if you take those 2 numbers and you compute the average density, you come up with some ridiculously large number, 5 times 10 to the 14 grams per cubic centimeter on average. That's like 2 times nuclear densities if you want to have a reference. So really what this talk will be about is to see what is inside of the neutron star. And contrary to what the name might suggest, it's not just neutrons. Actually, if you go to several times nuclear saturation, you can probe exotic states of matter, you can get strange quarks, so you get the hyperons, the sigmas, lambdas, and cascades. You can even get states of the deconfined quark matter. And so the interesting thing for our purposes is you have some blob of exotic dense matter flying around in space, and we want to know what's inside. For this, at least in this talk, we'll use gravitational waves. Okay, and so to give us some kind of picture of what's actually going on, we will look at one of those simulations now. And when we find ourselves just kind of, we're not waiting, I don't know, millions of years for the system to just orbit each other. Rather, we fast forward to 50 milliseconds close to impact. At that point, gravitational waves have carried out significant amounts of angular momentum and will ultimately drive the system to collide and merge. Okay, but whenever you want to do a simulation, or whenever you want to model such a system, before we get to watch the movie, there's one more thing we need to be clear about and upfront about. What's actually the physics that goes into making the movie, and then we can watch it. So if you wonder what the picture on the title slide was, that was kind of the first simulation I did as a grad student. In hindsight, I can say it's not exactly right, but the picture is not exactly wrong either. I'm sentimentally attached to it, so I like to put this on many of my slides. Okay, and if you want to model this, kind of the components you have to include first is general relativity, because you need to model the emission of gravitational waves. At some point, we will see if you put too much matter in one point in space, it might collapse and form a black hole. For this, you also need to solve the GR equations. So we will solve them in full dynamical relativity. On top of this, if we just had black holes, we could stop, but really we want to model the dynamics of dense matter. So we have to model the dynamics of the fluid. So we'll make a fluid assumption and solve the hydrodynamics equations on top and back reacted of the dynamically curved spacetime. And then in addition, of course, we need to tell the computer, well, it's actually nuclear matter and not just the coffee that I have here in my cup. And so you need to provide some description, and this enters in ideal hydrodynamics largely in terms of the equation of states as a function of the pressure as a function of thermodynamic variables. So it's density, temperature, and then we will see that composition here is very important. So what's the ratio of protons to neutrons in the system? If you want to capture the dynamics very accurately, in particular after the collision, you need to include electromagnetic fields, because those facilitate large amounts of the angular momentum transport, so you need to put in Maxwell as well. And then finally, because nuclear matter is special, it can have weak decays, you really need to include weak interactions. And I'll give some example towards the end of this talk of what this can actually do to the dynamics. It's quite interesting. And now, without further ado, or better say one more comment I want to make, if Einstein would live today, he would actually not probably stand in front of a blackboard, but he would solve all of this, because there's much more things you can do numerically than you can do analytically. So you can actually not solve all of this together.
So can you repeat it? What will Einstein do if
Einstein would probably like to do also simulations, because you cannot do this with pen and paper. Maybe, you know, he might not, but at least he might like people around to do that. That's my personal view. That's how I like to see that.
Numerical
This might not be a settleable question.
Exactly.
The speaker made a statement, I'm arguing.
We should get some historians if we have any
I've got a history.
preference there. But anyway, that's at least something that you could potentially do. And nowadays we can solve this. So I want to kind of start with a movie of this coalescence of two neutron stars. So let me hit play. We're about 50 milliseconds prior to impact. The stars are now orbiting each other, and I apologize for the poor quality of people watching over Zoom. The two stars orbit each other. What we cannot see is that gravitational waves continue to be emitted. They're driving the stars ever closer, and so you can see that they begin in touch. And right now they crash into each other, and you see that a lot of debris right now is flying out of the screen. What happens in the center of the collision, you form a hot blob of dense and really hot nuclear matter. It's kind of spinning around. It continues to emit gravitational waves because it's a bar-shaped deformation. Ultimately, then, you remove enough angular momentum so that the star can no longer stabilize itself against the pull of gravity. It will form a black hole and collapse, and then you have a black hole disk system.
Elias, what do the different colors symbolize?
She's on Zoom.
Oh,
That's
so the
fine.
different colors are density, and this is basically an artistic conception. So wherever you have the red color density has higher densities, the lighter color has lower densities. But I think the color map was chosen so that it looks more like a smoky kind of thing. So it's more like artistically, but it's correlated with density in the system.
Is it guaranteed to be a black hole, or it could be?
No, so we'll talk a little bit about this, but the end state will heavily depend on the initial masses that you start with. So basically, if you start with like a vanilla merger, like 1.4 and 1.4 solar masses, at least based on current observations and our understanding of nuclear theory, you will ultimately, after some time, collapse to a black hole. In this case, this would correspond to a more higher mass merger, maybe 1.6, 1.7, where you have this small phase where you form this hypermassive neutron star and then collapse. And if you go even higher, you immediately end up in the black hole. And this has strong observational consequences, because if everything ends up in the black hole, there's nothing that could power an electromagnetic counterpart. So the question is sort of how much matter is left and for how long does it stay up? Okay, what I want to do now is sort of as our kind of collecting all the things we've seen, all the things I've said so far on like a cartoonish picture. So I want to start out with, kind of classifying the different phases from the movie and assigning them to some observational windows we have into the system, and some results, again, with a view starting from dense matter that we have from the observational data that was collected already. So initially we saw that the neutron stars orbit each other, they emit gravitational waves, and we're lucky enough that this happens to be in a frequency band that's actually detectable. And so in 2017, the LIGO-Virgo collaboration announced their first detection of a neutron star merger in spiral, so this part of the gravitational wave stream. What's interesting about this in terms of having a neutron star versus having two black holes is that neutron stars deform in the tidal field of their companion. So basically the star is squishy, and this means that just as in the low high tide phenomena that you might encounter on the seaside, you basically get that the star begins to deform a little bit. That deformation gets imprinted into the gravitational wave signal. So what you can do is you can kind of correlate the size of the neutron star with part of the parameters that you can use to model the gravitational wave in spiral waveform. And from that, you can put direct constraints into how big neutron stars can be. This one.
So if the goal is to understand the internal structure of
Yes.
neutron star, is really that's the best thing to look at, or as a binary of neutron star black hole, because it seems to be more manageable, right?
So okay, so the full answer is there are several points to this answer. The first one is if you want to do this, there are other ways. This is also the X-ray constraints. So you could, for example, people have done like neutron star white dwarf systems. You can basically measure from the Shapiro delay of the pulsar radiation passing by the white dwarf, and then using Kepler's third law, you can do a direct mass measurement. For this, we know, for example, the mass of the most massive neutron star. You can do observations of hotspots. This is what NICER is doing. The instrument is like an X-ray telescope mounted on the International Space Station. That has put actually very tight constraints. And so people have combined them with the gravitational wave constraints. What is interesting, or basically what's the sort of more challenging thing with the black hole neutron star is in principle, you're right, because there's a degeneracy here since you don't measure individual. There's a property here, this lambda is like the squishiness of the star. You don't measure this individual number, but it's degenerate with sort of a mass average, and there are uncertainties there. But the main issue that you encounter in neutron star black hole is that basically this number enters at very high order in perturbation theory, like b over c to the 10th power. Right? In principle, then you say, is this even detectable? Well, it so happens that the coefficient in front of this is of order 100. And so then you kind of can do this because the coefficient is large, but it scales inversely with the mass of the system. And since black holes in those systems are most of the times much more massive, you kind of suppress the effect again. It's a very long answer to your question. So this is actually the best way of doing this with gravitational waves. And then what you can basically do is you can either correlate, this is more like the simplistic picture, if you get some idea of how big the star is, or in this other case, you get some idea of how squishy it is. You can correlate this directly via stellar structure equations down to what's the underlying nuclear physics. And again, here for this purpose, because we can ignore finite temperature effects because simply they do not modify the pressure substantially here because temperatures comparable to what we reach in the merger are too low. You're going to basically be able to put constraints on what nuclear matter is allowed to do, and you can relate this back and kind of say, well, what is actually inside the neutron star?
So the models, the equations of state on the right are the same as the lines on the left.
Exactly. There's some degeneracy there in how exactly you do that. You do that mapping. So being close for a pressure at one density doesn't mean that you're close in the mass radius space, because it basically also correlates with the slope of the curve, not just with a specific value. And so then what you can, however, do is you can do systematics. You can basically sample millions of models statistically or almost randomly according to some priors that you put that are consistent with nuclear theory and, let's say, X-ray observations, and you can kind of correlate back what happens inside of the neutron star. I just want to give you a visual impression rather than telling you exactly what's inside it, because that we still don't know. So it's still an open question if you would prefer deconfined quarks or if you had hyperons and so on. But what you can already see that from this one data point, a lot of the uncertainty already has vanished. And there are many, many versions of this figure that you find online. but in principle, this is something that we can do now. And the more constraints come in, especially jointly from the nicer observations of 2 pulsars now, this can even be further.
Sorry, this is just from the
This is just from the
in-spiral signal.
Yeah.
Okay.
But although this region there looks small, it is still highly degenerate. In fact, in this figure here, I had already applied the constraints in part.
Do the many versions I would find online overlap?
They overlap in depending. Well, they do overlap, yes. But the question is how well they overlap. And this is now a matter of taste. For example, if you prefer deconfined quark matter, what happens is you get a significant softening of the pressure. So this curve becomes very flat and then it has to become very stiff again. And that produces very low radii. And depending on what model people like and also what priors they select in this inference, you can kind of shift those shapes to the left and to the right a little bit. So we can roughly say, well, it's about 12 kilometers. And NICER, I think, originally had promised like 500-meter accuracy. It turns out to be more difficult for them to model the actual atmosphere of the neutron star to get that. But at least we have some idea of where it should lie. I think this is my current answer. All right. Let me go here. Then this is something that was not detected by LIGO simply because it's in higher frequency range. If you look at the gravitational wave strain at the top, you see that you go from the frequency range of the in-spiral, which roughly corresponds to the separation, down from orbital separation to size of the star. Frequency goes up. Again, we go outside of the sensitivity band of the detector, but now it actually gets interesting. If you think in terms of a neutron star merger as a cosmic collider, because you're similar to, let's say, like a heavy ion collision, you collide 2 neutron stars and you produce very high temperatures, up to 60, 70 MeV. And in principle, those are thought to probe the high density intermediate temperature range of the QCD phase diagrams. In principle, if you could access what happens in the stage, you get some idea of, let's say, how potentially quarks deconfine at finite temperature, and in general, how hot dense matter behaves, because your collision experiments typically happen at much higher temperatures than what the system probes.
What is this high frequency? Is it just rotation frequency of this blob?
It's basically a coupling between the rotation frequencies and the oscillation frequency, because you don't directly go from 2 stars to 1 star, you go to something that's bar-shaped and that basically starts to vibrate. And then you get a mode coupling.
But it is not just rotational?
It's not just rotational, no. You basically have, we'll see this later, you can classify this signal in terms of 3 frequencies.
But there are several frequencies.
Exactly, there are several frequencies, and you can then do spectroscopy with this in principle if there was a detection. Yes, that's right. And then ultimately what we saw in the movie, you can collapse to a black hole in this case simply because the system is too massive to support itself under the pull of gravity. If you remove enough angular momentum, the gravitational wave signal shuts off. But actually, the interesting part in terms of your electromagnetic counterparts begins just right now, because this system can eject lots of part of its mass, about 30 to 50%. This is very neutron rich, so it undergoes our process nucleosynthesis. But before we go there, one more thing, and I think we had this question before, like, in which channel we can actually go. Do we form a black hole or do we form the system? And this strongly depends on how much mass you can support in a neutron star before it collapses into a black hole. And actually, the interesting thing is, if you could distinguish somehow from the observation, either by absence of an electromagnetic counterpart, or if you had very large statistics, if you would see something, you could in fact put a constraint on how massive neutron stars can be. And this is something that I find interesting, because the numerical relativity community last year, actually several groups independently, have spent a lot of computational time and money to sort of figure out when exactly this happens, depending on the equation of state and the mass of the system. So that's something that we can actually infer with more data.
So these curves end because the thing collapses.
These curves end because the star would collapse.
Okay.
Yeah, exactly.
Right.
But there are these claims of astoundingly heavy neutron stars. Wasn't 2.85 from pulsar measurements recently?
Yeah, so recently there was one that they claimed to be, I think, 2.3 or 2.4 plus some uncertainty in this Black Widow system. But
and then yet another, I remember the central value is 2.85. It's mind-boggling. Maybe at some point you can address for us whether that's totally inconceivable from your standpoint and sort of has to be interpreted as an observational group.
Yes, I'll make a comment on this in one of the following slides, because there was one gravitational wave event with a 2.6 solar mass object. And the thing is basically that based on the 1708-17 discovery, or if you if you say, well, this thing had a short gamma ray burst, if you say you need high Lorentz factor and you need it to form a black hole, you can kind of check if, given those initial masses that you started out with, you can reasonably form a black hole given the maximum mass assumption of the equation of state. If you do this, then having any maximum mass higher than 2.4 is very hard. That's my take on it based on that event.
I have a more naive question, which is, do any of these curves depend on, like, do you expect all neutron stars to have the same equation of state, or is there some composition or something which contributes to
in principle, you might say, well, the neutron stars have different composition, but this is where the weak interactions sort of kick in. Because if you just put any type of, composition dependence that you would come up with by hand and you would put that in some space, then basically the weak interactions would try to establish equilibrium under the weak force. So in principle, the composition axis does not exist in this plot, because if the neutron star lives long enough, where long enough just means actually on a time scale of
days or something,
for something like even less than days, you basically equilibrate in terms of your neutron to proton ratio. The thing that some people have put forward, but that's more speculative, is imagine at a certain density, you would completely deconfine. There are people who believe that once you reach this, there's a combustion front that completely deconfines your neutron star into a quark star. That's more hypothetical and has many more issues, but in this case, you would actually have two different equations of state. You would have like something that's pure quark matter and something that's hadronic matter. But typically, you would expect if you go to high densities that nuclear matter would always behave the same. So assuming that the same equation of state is always valid in any star is a good assumption. But I think actually that the LIGO analysis team does not necessarily assume this in some of their analysis. So they have done inferences where they say, well, what if they're different? And it just enhances the error bars, but nothing fundamentally changes.
And how fast they rotate, doesn't affect this?
How fast they rotate, so basically it's interesting. If a neutron star spins very, very fast, you can at most get 20% more in terms of the maximum mass that you can support. And this seems to be largely independent of the equation of state that you have. Again, there's a caveat. If you have very strong phase transitions, maybe it's more like 27%, but 20% is a good number, because that seems to be a property more of gravity than of nuclear matter within the bounds in which we think nuclear matter should behave.
Is it fair to assume you ignore possible very strong magnetic fields threading the star?
If you had extremely strong magnetic fields of like 10 to the 17 to 10 to the 18 Gauss, they would affect stellar structure. But those are higher than magnetar field strength. So if this would exist, then yes, this would modify the equation.
You think that for real neutron stars, including magnetars, you don't have to worry about it?
Yes, so the modifications to the equation of state, I have a very close collaborator who spent like 6 or 7 years computing nuclear physics models with back-reacted magnetic fields. And for basically the equation of state itself to change, you need 10 to the 18 Gauss. And the more of the change of stellar structure is really because you have another contribution of energy density in the system. So from a nuclear matter point, I think we can completely ignore this. That's my understanding.
Sort of, is the rotation speed? I mean, you said it only changes the mass relation by 20%, but does it affect how long the remnant lives?
No, so how long the remnant lives will very strongly depend on the amount of angular momentum, because basically you can draw like a stability diagram of neutron stars, and depending on how much spin you have, you can be closer or further away from where collapse happens. So yeah, I think the main question is not only how much it rotates, but also how strongly differentially it rotates, because it will depend on like what the exact amount of angular momentum transport in the system is. Okay, exactly. And one more comment I wanted to make is there was a second detection of a neutron star gravitational wave event, binary neutron star merger gravitational wave event. And the interesting thing is that sort of with a total mass of 3.4 solar masses, it falls exactly sort of in this kind of question mark regime, but it more likely directly collapsed to a black hole or not. So this is really something that's also realized. This question is kind of interesting. The other thing that really kind of revolutionized at least this field was not just the gravitational wave signal that matters, but also all of the neutron-rich matter that gets ejected can power a wide array of electromagnetic fireworks. And so this is because if you eject a bunch of neutrons, ultimately they recombine into heavy elements, but those don't end up on the stable branch. Rather, what happens is that you get out-process nucleosynthesis and you get lots of decays, and the heat in this decay can power optical and infrared counterparts that have been detected for this first gravitational wave event. They can give you additional insights into how much mass was ejected, what's the nuclear composition, and you can then try to relate that back to what are the properties of the system. The other thing that happened was that in this system also had a short gamma ray burst, which likely was associated with this thing eventually forming a black hole, and then you can basically launch a relativistic outflow from the hole, and as it shocks the ambient cloud of ejecta, when it breaks out, you can power a short gamma ray burst, which happened about 2 seconds after the gravitational wave.
I think there's a question over
Yeah,
there.
sure.
For like the multi-messenger thing,
Yeah.
is there like in principle a neutrino counterpart proof then? Is it
No, so so the thing is basically that the environment is very dense. And so inside the star, neutrinos are trapped, and even they slowly more like diffuse out on larger parts. Yeah. I don't think anything was detected, or you would expect this, because this event is also very, very far away. It's like 30 megaparsecs compared to like, I don't know, a galactic supernova that would hit neutrinos. Yeah. Okay. And now this was one of the questions we had earlier, like what does this tell you about neutron star masses? I think I said something about that before, but basically the thing is, if you kind of correlate what mass you begin with, and then you assume because of the short gamma ray burst you ended up in a black hole, you can put a constraint on the maximum mass, and this is, we really tried to push this very hard, like how high can you go, but higher than 2.4 solar masses seems to be problematic. There is, however, a way around this, because this only assumes that you are non-rotating, and so if you have an event like GW 1908-14, which was kind of a very surprising event because you get the merger of a 23 solar mass black hole with a companion of 2.6 solar masses, where you don't know, was this a neutron star, was this not? If really it's 2.4, then maybe it wasn't a neutron star. The only way around this is if you add rapid rotation, because then you can get 20% more, and maybe you can stabilize that. But then you enter different problems, like how do you support very strong rapid rotation if you, for example, had pulsar spin down? Likely by the time of merger, you might have already removed that. So this is sort of a thing where I think it's more likely that you merged at merger, you had 2 black holes rather than a black hole. Okay, and then there's one more thing that I will at least give you my opinion on later in this talk is you could have another counterpart that's emitted either before or right at merger. This goes under the name of electromagnetic precursors emission. Earlier this year, there was a detection of a long gamma ray burst that was accompanied by a kilonova, and people said, well, maybe this is a gravitational wave event. So the detectors were offline, so you don't know, you don't have direct detection of gravitational waves, but the counterpart matches up. And this thing did have a precursor in gamma rays at around 100 keV, even quasi-periodically. So this is very exciting, but again, this is something new thing where we just have, again, one data point, but it might be interesting. And one of the things I want to show you later is some work on how you could basically get radio counterparts to this. And that might be very helpful. If you think in terms of you want to see all of those fireworks, you need to basically point your telescopes to where this event has happened, but then, and as rapidly as you can, but then the issue is that sky localization from gravitational waves might be very poor. And so some observers now are thinking, well, maybe you can do rapid radio localization with all sky facilities. That's sort of the context of this. And then what you can do, at least my personal take on this, if you want to model aspects of this, you want to connect all of those different observables to the underlying physics, the gravitational physics, nuclear physics, plasma physics, neutrino physics, you name it, you need to use simulations. And so what you need to do is you need to have some sort of approach where you can take the right-hand side as an input and compare to the data on the left-hand side. And what I want to do in the remainder of this talk, I want to give you some flavors of what I've been thinking about, or what other people have been thinking about recently in terms of this multi-scale multi-physics modeling of neutron star mergers using numerical relativity. Okay, and what I will do is I'll basically focus on 2 subtopics. The first one will roughly be on nuclear physics, but again, this time again on like hot and dense matter, similar to what happens in the collider. I'll also talk a bit about what neutrino interactions do, and then the second part, if we have some time, I'll talk about radio counterparts that you could have to the merger of the neutron stars. I will not talk about gravitational physics today, although there is a lot of interest in the community right now, largely actually for black holes, to think about modified theories of gravity on the simulation side. If you can incorporate those corrections and see in principle what would be upper bounds that you could place. But let me start out with the nuclear and neutrino physics here. And there the question again is, well, can you think of the system as a cosmic collider? It's really just like 2 blobs of nuclear matter colliding head on almost, if you factor out the rotation. And can you use this as a probe of extreme states of matter? What I want to do then, and actually did a comparison recently, literally putting side by side a gold-gold collision and a neutron star merger to compare this. The comparison is a bit more technical, so I spare you the details, but you get the gist that this is something that's potentially Interesting.
What is that?
That's a gold-gold collision. So there were some experiments close to where I went to university.
Like a gold
Yeah.
atom. and
Gold
then
ion
atom.
is
Yeah.
gold strip gold atom. You collide two of them, and basically there was a claim that in one of those facilities they had detected matter at several times nuclear densities, just like in a neutron star, but at temperatures that were a bit off. And so what we try to do is, if you use, in fact, the only description of nuclear matter valid in both regimes, like a theoretical model, you can actually run both systems and try to compare how similar they are. It is sort of a bit an unusual question to ask, but it's interesting. So there are interesting similarities in terms of the regime that you probe when those things immediately collide. And then gravity actually makes the system so different that anything beyond that
Don't
is
they
very
have
hard to-
dramatically different equations of state though?
Not so much actually. If you consider a low density, a low energy heavy ion collision. So I'm not talking about something like an ultra-relativistic heavy ion collision, but something that's roughly in the same ballpark. Then the only difference is that in the gold-gold case, you have symmetric matter. So you have, well, not exactly, but you have almost same number of neutrons to
The
probe.
densities are different.
No,
Like
the density is
neutron star
here.
denser.
No, the densities you reach in a collision are comparable.
Oh,
You
when
reach-
it gets compressed.
Exactly.
You mean. Okay,
Exactly.
okay.
And then you compare, basically, this is just showing the collision itself. So here you have two neutron stars colliding, and then you have two gold ions colliding, and there you reach like up to 2 times saturation density.
And both are hydro, really, right?
Those are hydro simulations, that's right, yeah. But the hydro is actually not, I mean, there is something like a pyromagnetic effect in the heavy ion case, but I think it's subdominant in terms of the impact, so that we can probably neglect. Yeah. But what we can do now is we can basically take the same movie we had in the beginning, but this time we focus more on what happens from the nuclear physics side. So I'll play this again. We don't bother with all of these things that does electromagnetic transients for astrophysical purposes. Rather, we will look inside the star at the point of collision. So right now, when the two stars collide, what we're going to do is we're going to cut them open, and we're going to show on the left-hand side the nuclear particles being probed. In particular, this is showing the amount of quarks that you have on a logarithmic scale. And then you can see that after the collision in this specific model, you get finite temperature deconfinement of quarks in large parts of the star. And now in the bottom inset, what I will show is a temperature profile, and you will see that wherever it's hot, you'll get quarks popping up, about a relative fraction of like 10 to the minus 3 or so. The more interesting that happens, and which is a bit hard to see, is as the density at the center increases, this equation of state has a first order phase transition. You literally get a deconfined core in the star, but nature isn't kind because it's gravitationally unstable and then it collapses. Okay, and so you can basically use this and ask, well, can we use future observatories for gravitational waves, like not NIGO, but something that we might have in 10 years, Cosmic Explorer or Einstein Telescope, to probe this high frequency part? And if so, can we associate features in the signal actually with the degrees of freedom in the nuclear physics at finite temperature? And the answer is maybe yes. So what I'm showing you here are two signals. One includes the equation of state with quarks, and then the other one is the same equation of state, the same nuclear physics model, where we just turned off the quarks by basically making them infinitely massive. And then what you see is that the signals after the merger, as soon as you get the finite temperature, appearance of quarks begin to dephase. And so in principle, yes, there is some imprint. Getting this extracted will require more systematic modeling. This is what I want to talk about now.
And that the difference in the later phase is like a few times the frequency of the in-spiral. Like it's not 100 times the frequency. Like it doesn't seem like that far out of band even.
No, so this the frequency in the in-spiral is below 1 kilohertz. And then out of band, yes, it's not 100 times. It's more like you go to 2 to 3 kilohertz, and then the detector rapidly loses sensitivity.
Yeah.
Yeah.
But I mean, it's like, but it's not.
No, it's not
totally inconceivable thing to do.
In principle, they could also sort of adjust the size of the cavity in the detector and make it more sensitive at higher frequencies. But then you lose out a low frequency sensitivity, and then you cannot do all of the statistics. That's interesting for like cosmological purposes. So that's something they're not doing right now, but that's something that might happen in 10 years. So what you can then do, or what ideally you would want to do, is you would like to systematically connect nuclear theories, so models, let's say for the QCD phase diagram or for the strong interaction, to those observables. And the way to do this, of course, is via numerical relativity simulations. But what turns out is there is a bottleneck. And the bottleneck is really, can we compute enough accurate nuclear theory models in order to simulate them and match them to, let's say, in the future gravitational wave signals, or to see what is their impact on the electromagnetic counterparts. And there, the challenge is really computing enough of those models. Like the equation of state I was showing you took 6 months to compute on a supercomputer, just the input that you need for the simulation. And there's some work going on that I'm involved in. This is led by the University of Illinois, the modular unified solver of the equation of state. What that's trying to do is it's trying to build a software infrastructure that can take a realistic nuclear model, rapidly vary the parameters, and then sort of output this in a usable format for LIGO, for the microactivity simulations, and for heavy ion collisions. So there's some work going on this right now, and we hope to have,
Sorry, what is the goal? It's here a bit rapidly. So you said 6 months now. What would
I think
you,
right
what
now
would
they
you-
have already optimized like that prototypical code, and I think the compute time is a week or something. And I think they're pushing this further. Like basically the idea that the promise of Muses is that at some point you'll have a web service where you log in, you say, this is what I want, you hit enter, and then you wait a little bit and you download the file. That would be the goal. But I think we're still 3 years away from this, but at least part of the software infrastructure already exists. And then to give you some flavor of how this works, maybe this is too complicated, but one thing that you can do is you can ask questions for how does nuclear matter behave around saturation. And there's some equations there. It's probably the most complicated equation I have on all of the slides. But basically what I'm saying here in one of the models, because physicists like to series expand everything they have, you can series expand the binding energy per nucleon, and then you can basically look at the linear term in this, and you can say, well, if I have some constraints from a nuclear experiment, basically from electron scattering off of lab atoms, you can get a constraint on what this is. Anyway, what we did here is we said, well, since there is an experimental constraint from the PRX experiment, they look at basically the neutron skin thickness of lead. You can say, well, can we systematically put this into such a simulation, get some constraints out? I'm not going to talk to you about all of the details today because this is, again, more technical, but the answer is yes, we're actually at the point where we can do this. So this is basically the different columns are different parameters, different models for this nuclear parameter. You basically see there are differences, we analyze the gravitational wave spectrum, and so on. And I want to take this as a motivation and basically pick up the question of how would you actually detect this? What are, is this just a rotational frequency? And what you can do is, you can take this gravitational wave strain and you can just look at the frequency space. So this is what's shown here. At the top, there's the time domain gravitational wave strain. At the bottom, there is the frequency spectrogram. And you see that there are 3 different peaks in the spectrum, F1, F2, and F3. And they might be more prominent in different cases, but the interesting thing is F2 because that's always there. And then you can basically ask if you use a different equation of state, that's the red line, what you get completely different spectrum. And so the idea would be, if you could measure the frequency contributions, you can basically relate this back to what equation of state you have. And here, GNH3, I think, gives you bigger stars, and APR4 gives you smaller stars. So there's some correlation with the radius there as well. And really, you should think about this as, identifying elements, for example, the solar chromosphere or so, at some point. This is not as random as it sounds. It's not that you have to look at, all possible equations of state. Rather, what people have shown is that there is a universal correlation. So this main peak, that's always the dominant one, seems to have a correlation with the squishiness parameter from the beginning of the talk. So if you start out measuring your in-spiral signal, you have some idea where you end up with, and then you can make a comparison. But there's still more work to do because in principle, as you can see, this relation, this quasi-universal relation has a lot of scatter. And this scatter, whether you basically fall above the mean or below the mean, also tells you something about the properties of dense matter. That's something that we did recently. This is a study together with Karen Rathel at the Institute. Where we looked into what happens if you fall above or below, and there seems to be a systematic correlation with whether you end up with larger stars at high mass or smaller stars. So there seems to be an intricate correlation that points that fall below the curve have mass radius curves that have larger radii at high masses versus points that fall above the curve that have smaller radii at high masses. A very extreme example would be if you have a complete deconfinement at merger, then you end up at really, really small stars, and this has been shown before to violate those correlations. But overall, what you need to do is you still need to do more simulations because this is something where you really need a lot of data. You need to have all of the errors of the simulation under control, but we have more than 10 years time. So I think we're on track.
And so this correlation, is it something one can understand with pen and paper? Or?
People have tried to understand it with pen and paper, but the difficulty is basically if you have an equal mass merger, things get easy because the things collide and you have like 2 centers of the former stars that oscillate, and then you can kind of make a toy model of like things with a spring that rotate. It's more difficult if you have a significant mass ratio, if one of the stars is almost 2 times heavier than the other, because then you get tidal disruption. And then it's more like looking at modes of an oscillating star. If you're in between the analytics are more complicated. But people have tried to do this, so there is at least some rough understanding, but there's no conversion, I would say. Yeah. And then one of the things I want to highlight now, and this is really going to what are the uncertainties in doing this, because the system is so highly dynamical, there's so many physics playing in. For example, if you have exotic degrees of freedom, things might change. You get uncertainties in this model of like 100, 200 hertz, and this is what we saw in the earlier plot. If you add in finite temperature, you get basically differences of the same order. So because here really nuclear matter is hot, it's not just a single line, it's many lines, and they depend on the temperature in a not so trivial way, at least at high temperatures. And so this might affect this relation as well. Then magnetic fields, we're doing astrophysics, so magnetic fields always have an effect, but seriously they actually do, because if you have small scale turbulence during the early merger and you have large amplification of magnetic fields, they might change the internal structure, they might cause additional damping and angular momentum transport, and that might affect these relations too, roughly on the same order. And then you can also have neutrino effects, and this is something that I want to talk to you right now. And this is really, think of this more as the chemistry inside the star. Okay, so if I basically start rapidly changing the ratio of neutrons to protons, depending on decay processes that I have, this will also have an effect. And this is very interesting, both in terms of the physics being proved, but also their connections to what actually happens in a heavy ion collision. So there's even a more fundamental question you can ask. So the main thing is that nuclear matter, if you look at those two reactions, neutrons can decay to protons, and then you can have electron capture, so protons can go back to neutrons. And ideally, those two reactions balance, as we discussed earlier in the spiral. But then, when the two stars collide and you rapidly change density and temperature, they no longer do. And so you basically go to a state where you have an equilibrium ratio of neutrons to protons to a state where you end up with something that might be very out of equilibrium. And then you get this chemical process, effectively, of the star either neutronizing or protonizing, and that depends heavily on the properties of the equation of state and the merger itself. And this might change the dynamics of the system, and has been conjectured that appears as a bulk viscosity. So basically the thing is oscillating. If this happens, it's oscillating less. Okay. And what we did recently is we actually simulated for the first time what happens if you put those reactions self-consistently in the merger. And this is really kind of making the simulations more realistic from the physics. To give you some background on how this works, I'll introduce one number. This is kind of the out of equilibrium chemical potential. Basically just say if those reactions balance, delta mu is 0. If they don't balance, delta mu is non-zero. Okay? And then you can ask how large is this number, depending on the parameters and properties of the simulation. So putting into one curve what I said in words, before the merger, everything in terms of this ratio of protons to neutrons lines up basically on one curve set by the equation of state, and effectively by the pressure at nuclear densities. Then, as you go through the merger, those points here basically go away from this line, and then the chemical reactions set in and cause a dynamical feedback on the system, okay? Trying to basically push it back. And so what you can do is, you can do this with real simulation data, and then you would see if you were in equilibrium, you get this red line. If you don't put the right neutrino physics in, and this is what most people, including myself, have done until recently, you end up with the gray line. And then you basically see that you would predict that you have inside the star 10% protons, but actually it can go up to like 18%. And that has a very significant effect on the dynamics of the system, the lifetime of the system, and on the gravitational wave emission. And the way we quantify this, we used some terminology coming from nuclear physics, because in a heavy ion collision you have the same, but there it's not because of neutrino physics. There it's because you basically truncate the Boltzmann equation. Ideally, you would have to solve the collisional Boltzmann equation, but you truncate this, and so you get anisotropic pressure corrections. The lowest one gives you a bulk viscosity sort of type correction, and we use that kind of terminology to estimate how large this can be. And so basically, just in color, here you get a very large correction. So right when the stars tightly deform, you're very out of equilibrium, and then a few milliseconds later, kind of color gets dark, and the correction disappears, and basically the chemistry has burnt, so to speak, the interior of the star, and in this case, I think has protonized it. And this then corresponds to a correction. Let me fast forward.
What does the word protonize mean exactly?
What this means is you basically have a number of neutrons to protons. When I say protonize, I mean that neutrons, some of the neutrons turn into protons, so that the system is more proton rich. When I say neutronize, some of the protons turn into neutrons, so that the system then increases this neutron
And
fashion.
you have some electrons running around too, presumably.
In this model, you have some electrons running around too if you use more sophisticated
but
models.
it's charge neutral.
Yeah, the system overall has to be charge neutral.
Okay,
Yes.
good.
Yeah, that's even the fundamental assumption that we bake in. But conductivity in the system is so high that there's no significant charge separation anyway. Yeah, exactly. And then you can see that you get similar changes in the post-merger gravitational wave signals. So that's really an effect that you have to take into account, and something that with those next generation facilities you might actually be able to discern. So that's really interesting, and it's something that can actually be solved because you can, from nuclear theory, compute for many, or essentially for almost all equational state models, you can compute how this process should proceed.
So can you explain?
Yep.
Just go back to that plot.
Sure.
What's the bottom plot?
So the bottom plot is two different equations of state. I should have said that. So in the top you have SFHO, that's one model that gives you smaller stars. Then you have TMA that gives you larger stars. What is interesting is that in terms of the symmetry energy parameter, they're very different. And that basically means that the strength of this effect is much larger in this case than in that case.
I see. So these are two different equations of state, and then you're adding in each case,
In each case, we're adding the physics in.
Yeah.
And then we basically had like a prior expectation of which case would have the stronger effect. We got a little bit surprised by what we found, but in principle, it still holds that the lower case has a stronger effect than the upper case.
When people do, you said you weren't going to talk about gravitational physics,
Mhm.
but when people do those studies, should they be worrying about the degeneracies in this?
Oh,
level of
they largely
modeling?
do this with black holes to start with, so that,
Oh,
that
that's
makes
probably smart.
you have much larger statistics,
Yeah.
and you don't have to worry about this. But yeah, if you wanted to do this with neutron stars, there was a recent study where I think I know of two studies where people did self-consistent models of neutron star mergers and modified gravity. There are also studies where they did neutron star mergers with dark matter. So basically, you just have like a halo of dark matter around the merger that you model as a scalar field or so. And then you get similar orders of deviations. Yes.
Okay.
So if you don't believe in Einstein, you cannot do this, or vice versa. You have to be very confident on your nuclear physics if you want to do modifications of GR. Yeah.
Okay, yeah, but obviously you're right. They use the black holes.
In the second plot, it looks like as if the amplitude of gravitational waves is increasing with time, at great time. Is there
So what basically happens there is that the two models are slightly different in size, because it's not just that you change the chemistry of the star, but also the equation of state depends on how many neutrons and protons you have. So there's an overall change in structure just because you change composition, and this is why the amplitude changes. And it's much more pronounced in the lower case, is what I was trying to allude to, than in the upper case.
I don't understand the sense. I mean, why is the amplitude increasing? Forget this out of equilibrium chemistry. For the second equation of state, it looks like, as Yasin said, that the amplitude of gravitational wave is growing at late time.
Yes.
Is it a simple thing to understand?
Yes,
or?
because the size of the star changes. The thing that we initially thought is it's just going to act as a bulk viscosity, so just going to dampen. But what you find is because you change the overall equation of state by changing the composition, you also change the effective size of the star because the pressure increases.
so you have a larger quadrupole moment?
Yes, it's basically just correlated with that. Yeah.
You didn't really tell us what the different plots were. If you did, it was so fast I couldn't grasp it. Could you just, so we can learn something from the comparison, could you tell us what the different physics models were?
Yeah,
SFO and TMA?
Yeah, the differences in those models is not too important. It's just two different models that differ basically at lower densities and what happens around nuclear matter. The interesting thing in this model is that there's basically always a light curve and a dark curve, and that corresponds to whether you have the neutrino interaction that's given at the top included or not included. And this reaction should be included, but it hasn't been so far. And what I was saying is, if you don't take this into account, then you basically get the wrong signal in some sense, because you're missing out the right chemistry.
I understood that part of the point. Thanks.
Good question. Yeah, thanks.
But neutrinos are still trapped inside of this thing. They're not carrying the lepton number super quickly away.
In large parts of the star, they're trapped because most of the matter is in a neutrino trap regime because you have temperatures that are very high. And so basically what we do in this model is we say, well, if you have temperatures higher than 10 MeV, we assume that stuff is trapped. Yeah, but we actually don't have to assume this, because if they are trapped, then basically the matter equilibrates instantaneously, because the rate at which the equilibration happens in this process scales like T to the 6 or so. So there's a very high temperature difference. All right. Okay. Enough of nuclear matter. I think in the final part, I know we only have a few minutes left, and it's good that we had a lot of discussion. I want to talk briefly about what happens outside of the star in terms of potential radio precursors. And the idea there is, so far we looked inside the star, but now we're just going to zoom out. We're going to ask, well, actually, it's not just extreme physics in the star, but the star is surrounded by a very conducting electron-positron plasma, and that can do interesting things. You can think about modeling a pulsar like this, for example, of course, for electrodynamics. And now we're going to ask, if you have two stars with such magnetic hair, what's going to happen close before they merge? And so for this, we're going to look at the following system. We have, again, our two stars here, just schematically, and in red, what I denote is the orientation of the magnetic moments. One has basically, if you think in terms of dipole, one dipole is pointing down and one dipole is pointing up. And in that case, in this conducting plasma, you can have connected field lines. And now what will happen as the stars just move around, you can get differential rotation in the system. Even if you just have an irrotational system, you'll basically have this. You're going to build up a twist in this magnetosphere. And ultimately, if you twist them, the field lines, they can do something, they can snap, they can feature magnetic reconnection, and interesting things may happen. I'm going to show you that in a second. If you want to have a more realistic picture of how this works, is if you look at our sun, there's something called solar flares. We basically have foot points. The foot points have a relative twist. The field lines begin to inflate, and you get such a loop going to build up. And at some point, this loop is going to be ejected, and the same thing can happen in a neutron star binary if the topology is similar in terms of one of the fields pointing up and one of the fields pointing down.
Isn't the fluence obviously not enough to detect on Earth from all these megaparsecs?
Well, actually, what I'm going to say in a few slides is we have found a mechanism where you could produce FRB-like transients from the interaction of the flare.
Only FRB, right? Not
yes.
GRB. FRB.
Not GRB, not GRB. That's right. Yes, FRB and potentially X-ray, if you get that from the reconnecting current sheet. Yeah, that's right. And this is the thing that where I said it wasn't discovered yet, but people are actually looking for this as a new means of improving sky localization. So what I'm going to show you now is a simulation outcome of one of the simulations that I did when I was at CCA a few years ago. And there, what you can see is you again have these connected field lines, and in color, I indicate the out-of-plane magnetic field. This indicates how much you have twisted. So wherever you have darker colors, you have more twists. And then if you start the movie, you're basically going to see if you twist long enough, and this is just by the orbital motion itself, you periodically, before the merger, will launch electromagnetic flares. And in this case, they're aligned such that they basically go out in the polar direction. But if you have, let's say, magnetic fields that are inclined, you will have the flares being beamed more in the equator. And you can do estimates. And we actually found that you can have, for realistic events, if you have 10 to the 11 Gauss, and you had such a configuration, maybe you might be able to have 20 of those flying events that are strong enough to produce a radio counterpart, in principle. And I'm going to tell you in a second of how that
Although,
actually
of course,
works.
nobody has any idea what FRB is coming from.
No, I'm not saying this is explaining any FRBs, right? I'm just saying that this particular system might do an FRB-like transient. I'm actually going to tell you, if it does, likely this happens in the range of 10 to 20 gigahertz, which is higher than for current FRBs. So this would be actually very distinct, if it works. But this was kind of the estimate, sort of, yes, something can happen. It has a very nice kind of toy cartoonish picture of what's going on, but really now we have to talk about the emission physics there. Andre is very right. And just to make the point again, people have actually tried to detect this for the 2017 event. This is Callister et al. At the Ovro Observatory. They have tried in the megahertz band to find something. So they have an all-sky observation where they basically record data for like several hours, and then they just dump the data and we're like, okay, can we find something or not? And the answer was for megahertz, they didn't find anything for the 170817 event. But people are looking for this because it would help you with the localization itself. And here, I'm not sure if you can see it, you actually see the uncertainty that they were facing. So if something, the gravitational wave event was predicting something should happen in this band or not. And then if you, of course, would say, well, it's right here, because there's something that's coincident or has the right properties, that might be interesting. Okay, now how would that actually work? How do you get something out that we can see with a telescope? And there the question is sort of what's the actual emission process in this system? And then we had a recent study that I want to quickly highlight, and I think then we can take some more questions. The idea is that this flare, as it propagates out, just doesn't propagate out in vacuum, rather there's still the electron-positron plasma around. And what can happen is that since the moving star, just like a rotating star, also if you just move around a dipole in an orbit, will have a current sheet. So this is basically a region of outgoing charge that separates oppositely directed magnetic fields. The flare can hit this, and that can basically cause the fields there to reconnect, which schematically would produce you these little magnetic islands. And then the merger of those islands gives you a time-varying current on their size, which is like centimeters, and then you would get radio out. That's the basic picture behind this. And so what we found actually, we found evidence in the simulation itself. It's not something we were looking for. We found this more by pure chance, that this actually happens. The flares can be such that they hit the orbital current sheet, cause this compression, and then produce a radio transient as a result. What I want to show you, this is a bit cluttered, but this is actually a simulation. So I'm going to slowly walk you through it while this is playing. So those are the two stars. We're sitting on the stars as they're spinning. This is the equatorial plane. Here you see the toroidal field. So this is basically showing you the flare. So you're periodically launching these flares. And I apologize for people on Zoom, since my mouse pointer is not working, I have to do it by hand here. Things that the flares are propagating out. And ultimately, in this point, this is showing you the dissipation rate. They hit the orbital current sheet right over there, causing these overdensities to form, and as they collide, you get, in principle, a radio signal out, if the parameters are such that you end up in the right regime, okay? And this is really something what I really like about this is where the simulation told us what should happen rather than us coming up with a model of like, oh yeah, we want radio, this is what should happen, which I like a lot. And here what we did is then, we repurposed a model that was a little while back proposed by Yuri Lubatsky for magnetar emission, for linearly polarized FRB from magnetars, where it was basically saying, well, you do have some sort of pulses coming from the star that compress the orbital current sheet. He worked out all of the analytics, and what we did was we basically took that simulation, painted on the values, and then you can compute what sort of the emission that you get when this repeating flare hits the orbital current sheet, and the answer is you end up with something in the range of 10 to 20 gigahertz for magnetic field strength of about 10 to the 11 Gauss. So below magnetar field strength, because here the flare is launched from further out, so you need less field strength, and you would get a very, on the lowish end in terms of luminosities, I think you get energies of 10 to the 38 or so, 10 to the 37 Hertz. But the interesting thing is it really happens in a range that is higher than current FRBs. I think the highest FRB is like 8 gigahertz. So this is really something that's potentially interesting.
Sorry, your voice dropped a little. Are you saying that these cannot explain the presently known radio bursts?
Yes, this would be a new population of radio bursts at higher frequencies, yes. And the unfortunate thing about this, of course, is that most FRB telescopes are not sensitive in this range. They're sensitive at 1 gigahertz. But for example, the SKA in South Africa will have frequency coverage up to 24-ish gigahertz, depending on how much money they're investing. So this would give you a
rate like?
Sorry?
I mean, do you have any estimate of the rate of observable events, let's say with SKA? Because at least you have an idea of what the rate of the neutron star mergers is.
Yeah, the big uncertainty that this is something that we're still trying to figure out. For the model that we considered here, everything lines up perfectly. But the question is sort of, do you get this generically for any magnetic field configuration, which we have almost no handle? And the answer is no. In this case, I mean, you need something that's at least pointing in opposite directions. And you need to make sure that the flare hits the current sheet at the right point, because if it hits it too far out, the magnetic field strength is too low and you end up in the wrong frequency band, and you also have lower energy. And so this is something we're still working on. I cannot make a good rate prediction. I can just say that some models will fall in this range, but we have to do more modeling to be sure how general this is.
Yeah. The statement that it's higher frequency than the FRBs, how robust it is?
This is pretty robust within. There's some uncertainty. We could even push it down to 1 gigahertz. The main uncertainty we have is the location where you hit the current sheet. And this will also depend here, one of the stars is spinning. We didn't set this up in this way. This happened naturally, which is a good sign. And we have actually a companion paper that studies many field inclinations and shows that you get always these flares. They differ in energy only by a factor of a few, but we haven't systematically looked at where exactly the flares hit the current sheet. So take that as an indication. You might go in this range, but it's an interesting indication.
how long before the merger do these flares start happening?
Yeah, so the main issue that you have is that there seems to be a very strong scaling of the energy in the flare with the separation that goes like 8 to the minus 3.5, is what we fit from the simulations. And so we estimated that you can get at most 20 flares, and this is really based on the last orbits, making sure that you get enough energy out for this to do anything sensible. Yeah, so it's really something immediately at merger. Okay, I see we already have 3 p.m. So I had planned another few minutes on the modeling aspects, but I think we can also shift this to a one-on-one discussion if people are interested in the closely
why
official
don't we
part.
thank you, take
Yes.
questions, and allow people to move on if they have things to do, and people who want to stay and listen to more modeling details, we can do that. So let's start. Are there any additional questions? Because we were very shy during the talk.
I mean, I'd be interested to hear more about the modeling of this and like how you handle reconnection, like what kind of model you're using and that sort of stuff.
Yeah. Okay. How about we wait like 2-3 minutes and then I can show you those parts. Yeah. So right now, I mean, this simulation is
Actually, at this point, I'm going to stop the recording.
Yes.
Yeah, that would be
Sounds
that.
good.